we actually, what I probably have something from the past. Graph. This is from this. Oh. Reese, if you if you don't have further question, you can go. What for Rafi, what specific question about the scheduling assignment that you have? Okay, Reese. Good luck to your quiz. You too. Have a nice day. Nice to have you here, like always. So, Rafi, may I know which specific questions do you have about? One graph for both of the questions. Suppose there are 5 classes, only 5 students wishing to take the following. There's only one graph. You don't need 2 graphs. The chromatic number is the minimum number that you use to color the graph. So here's some example here. You see the screen, right? Yeah. Okay, so here I have different vertices that have different color. Graph coloring, we color the vertex. We don't color the line. Okay? So a graph has been colored if the color has been assigned to each vertex in such a way that adjacent vertex have different color. So if two vertices is connected, then you cannot color them the same color. For example, this graph is color, okay? The blue and yellow one's connected, so you cannot color the same color. So yellow and this one is connected. So as long as it's not the same color, this two is not the same color, that's fine. Okay, this two is not the same color, so that's fine. If it's connected, it cannot have the same color. So you want to use as minimum color as possible because it's for scheduling. You don't want to have too many slot open, then you use more resource to support more classes. If you can use the same color that you used before, then you use that. So in this case, I start with dark blue and then I use yellow. So the next one that I connected, I want to use the same color if I can. So when I try to color this light blue, I say, okay, it's connected to yellow, so I cannot color yellow. It's connected to the blue, so I cannot color the dark blue. So I have to pick different colors. So I pick a light blue. Okay. Now I want to color this vertex. This vertex is connected to the yellow, so I cannot color yellow. It is also connected to the light blue, so I cannot color light blue. But it's not connected to the first dark blue, right? So it's not connected to that, so I can color dark blue. Meaning these two classes, in this case, the class that the assignment we're talking about is class, can be scheduled in the same time because they're not conflict. So to color to the last one, I compare my adjacent vertices. I cannot have the same color. It's connected. The three adjacent vertices has three different colors. So I cannot use either one of them. I cannot use dark blue. I cannot use light blue. I also cannot use yellow. So I have to use a different color, which is orange. So count how many colors do we have in this graph? The minimum colors. How many colors did I use? No, the color will be blue, light blue, yellow, and orange. 4 colors. So 4 is a chromatic number. So the chromatic number of a graph is the smallest number of colors with which it can be colored. And the chromatic number represented in our scheduling problem is how many slots of the classes that Mrs. Jacobs have to have so that no conflict would be. If two vertices are the same color, meaning they can be scheduled in the same time. Okay, so I need to have at least 4 slots in my example here so that everybody will, so that there's no conflict on schedule. In this case, given whatever the situations are. So if you have a graph is a planar, it can be drawn on a plane without edge crossing. Okay. The 4-color theorem. So these are all like just main point. I only give points in this presentation. If you have a map to color, a planar graph, which is there's no crossing. Like, okay, for example, this is not a planar graph. There's one edge is crossing. They are overlapping each other. This is a planar graph because there's no overlapping edge. Okay? A map is a planar graph. A map. For a planar graph, the maximum number that you need is 4. Or you can use less than 4. This was the conjecture in 1850s. Conjectures mean people think, oh, this might be true. But after they proved it in 1976, using computer-aided program, it became a theorem. So it's a theorem means you can just use it. It's a truth. It has been proven. Here's a page that you can get more resources. A tree graph and a graph with no cycles and a graph that look like a polygon with, if n is even, 4 or square, or if the number of edges is even, then you can always color with 2 colors. Okay, if the end is odd, you cannot color with two colors. Meaning the graph after the edges are connected, it looks like a polygon. You can make it like a polygon. And if the edge is odd, then you cannot color with two colors. If the end is even, then you color with two colors. Like a square, right? You can color the both sides with one, the vertices with two colors. So make sure you study the content, and here are some extra links for you to study. These are links that you don't need me guide you through. You can just study it. More example, page 3, 4, 5 for more graph color examples. You should click the link and bookmark it. Let me see. I haven't uploaded this because this was, I was gonna do it later. Since you're here, I'm just gonna do it. So let me see. It probably got some defects. So I uploaded this PowerPoint at the bottom part. It's called, it's another July 5th. It's the last one. They have 947 kilobyte. So let's see. So you want to see some example of graph coloring the map? Hi Joshua. Welcome to the office hour. We are reviewing graph coloring. It's what's happening today and tomorrow for the test. So I'm about to show an example of coloring the graph. And if you're here, make sure you download the PowerPoint that I'm going over at the bottom part. You see a chat box below the chat box. That is a file part. You can download the 2016 July 5th graph color folder. So we were just talking about for any map, right? You can color the map with only 4 colors. So for example, this map, can you see the map on my screen? I can color it with different colors, but I want to use the minimum color possible. The minimum color that I will use is called chromatic. The number of minimum colors that I use is called a chromatic number. It's in the previous slide of this PowerPoint. So let's start with red. Okay, I color this one red. And then whatever it touches its edge, I cannot color red. So I have to pick different colors. Let's say blue. Hartford, I color it blue. So I cannot color New Haven blue because New Haven touches Hartford edges. But I can color Fairview blue. I can color this one blue because it doesn't touch with the other blue that I color. So the next color I pick is green. I'm going to use green to color New Haven because it touches red, it touches the blue, so it has to be the third color. Now I'm going to color this section right here. Can you guys suggest me what color should I pick to color this section? This state, this. Well, you want to use minimum color as possible. If there's color that I already have that I can use it there, I will use the one that I already have. That's right. You use red. You got it. Okay? I mean, of course you can color the whole map all different colors. Okay, now I want to color Toland, this section right here, right? Look at the edges, make sure it touches only this one, which is the blue one. So what color should I color here? Green? Good. Now I want to color Windham. Where should I color? What color should I color here? Blue. Okay. Now I want to color New London right here. What color should I color? Oh, sorry. I'll try to make it big to show you. Orange. So he see that because this state touches the blue, the state that color blue, I cannot use blue, is on the border of the state that color green, I cannot use green, and also I cannot use red either. So I have to use orange, a different color. It doesn't have to be orange. So good job. So how many colors did I use in this map to color this map? 4. And 4 is what we call our chromatic number. Okay? It's our chromatic number. It's a minimum color I use to color a map or a graph. Okay, now let me pull out a different one. You guys get this? If you get this, I don't have to do more example. This is not hard, right? You just need to be careful. And when you are doing a quiz in a test, you have what's that called? You know, it's a computer screen. You cannot really color the computer screen, but make sure you sketch it out on the paper, because sometimes state like New London, that if you're not careful, you might not see that you cannot actually color one of the 3 colors that you already picked, and which some students make the mistake before. So I'm warning you right now. So make sure you sketch it out and color it. Simple questions that you can have. So this is just more example. This state also you have to color with 4 colors, and you don't need more than 4. It's just 4. Minimum colors, that's what I'm saying. Okay, so this is just extra example. So look at these questions. This is just simple questions right here. Which vertex is adjacent to vertex C? A and D and E. Good. So let's see. I'm gonna give you guys some drawing power that you can draw on my screen. Do you think you can color this graph? Joshua, let's you guys work together to color this graph. Remember, to color this graph, a graph that's adjacent to each other cannot have the same color. Okay? We color the vertex, you don't color the edge. Forget about my scribbling here. I don't know what I did before, but you just color the vertex. Both of you have coloring power now, so you can actually draw on my screen. Pick different color. Let me just assign. Joshua, you got purple. You mentioned purple just now, and Rafi used orange. Color the vertex. Actually, you should probably need to use more than 2 colors. Pick your own color. Click the color palette, and then you pick your own color. We probably, because the graph coloring, we might need to use more than 2. Okay, we start C with purple. So any vertex that's next to C cannot be purple. Okay, I do not color the edge, only color the vertex. So you guys work as a team to make this graph look right. Yellow sounds good. So good. Whoever who did it is doing a good job. So what should B be? It can be yellow because it's not connected to A. It is not connected to E. That's yellow. Good. So where's the chromatic number? Three. So if A, B, C, D, E are classes, okay? If A, B, C, D, E are classes, which class cannot be scheduled at the same time? Give me one example. Which class cannot be scheduled at the same time? If they're the same color, meaning they can be scheduled at the same time. If they're not the same color, they need to be scheduled at a different time. They can be scheduled at the same time because they are not connected. Depends. It depends on your what's it called, the criteria that they give you. Okay, if you connect them because they can be scheduled, then at the same time, then you have to think about a different way. But this graph is connected because they cannot. So in this case, for your assignment, if they're connected, okay, they cannot have the same colors. Okay, so if they cannot have the same color, in this case, like your scheduling problem, they cannot be at the same time. They cannot be scheduled at the same time. So we need, because our chromatic number is 3, so we need 3 slots. Okay, the first slot has class A, second slot class B, is 3. So you can, class C has to by herself, second slot class D, and then A, B, and E can be in one section, can in one period. A pair that cannot be scheduled at the same time? If they don't have the same color, they cannot schedule at the same time. BD, AC, ED. Oh, well, this is this. I was just, well, we have the assignments that was supposed to be due today, and that's where Rafi started asking, and that's how I started discussing. Let me see. I think I have more example. But the idea is, if they are the chromatic number decided, help you to decide how many period you need to have, minimum period of scheduling. Okay, final exam or section for classes, so that students don't have conflict. If students take the same class, I think in the scheduling problem, if they take the same class, you have to draw a line. That's the age. If they take the same class, let's say Joshua take class A and D, and Rafi take class B and D, then you will draw a line. So if you take class B and D, you cannot do class B and D at the same time. So that's why you color them differently. That's why they are in different slots. That's why you go to them in a different time. Rafi, did I answer all your questions about scheduling problem so far? Okay. So here just some extension practice question that's similar to the quiz and test. Okay. Now we understand if yeah. So let's see. Here's the answer, but don't look at it. Don't look at the answer. Do it yourself. On the graph, because I was gonna do this later, but since Rafi is here, I'm just gonna do it now. Which vertex can be colored the same as vertex F? There'll be more than one. You tell me, you type in the chat. And you need to understand why it can be colored the same as vertex F. So vertex F is right here. As long as the vertex is not right next to F, it's not connected to F, it can be colored the same as vertex F. Okay? So F is right here. I color it red, yellow. Okay? And I cannot color D yellow. I cannot color C yellow. I cannot color E yellow. I cannot color H yellow because they're all connected to F. But I can color G yellow. If I color G yellow, I cannot color A yellow because A is connected to G. Okay? Then I can color B yellow because B is connected to A that's not yellow, but it's not connected to F, so I can color B yellow. If I color B yellow, I cannot color C yellow. Okay, so either G or B can be colored the same as F. That's one choice. That's a different choice. Let's say I color F red. That's a different choice. So since A is not connected to F, and if I did not color G red, I could color A red. Then I can color C red too, because A and C are not connected. Oh, I cannot color C red because C is connected to F. But I can definitely color A red. Okay, so if it's yellow, you have G and B. If it's red, you have A. That you can color the same color as vertex F. Question? Confused? These are the kind of question that could be asked in the quiz. Simple. If you understand the concept, it could be simple. Okay, now for PERT, this is a different topic. Since you're here, PERT is the next topic you're supposed to do tomorrow. You can listen up, and after, if you haven't studied, and then after you look at the content, you might have a better idea. If you have studied, and like Rafi, he's planning to take the test today, I will just, Rafi, have you looked over the content of PERT? Okay, so, let me see. I think I have some video of it. Well, after our session, I might post some extra resource under news, okay? So here's a note on PERT. You can click on that. It cannot be clickable. Well, you cannot click on that. Well, in your level of PERT, okay, PERT could go up to very sophisticated. But in your level of PERT, what you have to do is you are given a list of activities, okay? And in this list of activities, I tell you in your assignment, the assignment tell you which activity should happen before the other. Okay, you have to do this first before you do this, and after that you can do this one. Okay, and some activities require 2 or 3 more things to be done before it could be done. And then you are also given expected time. How much time each activity will be done. So you don't need to calculate this. You don't need to figure out the sequence of tasks. You don't need to calculate the expected time. And you already have the list of activities. Okay. In real life, if you are project manager, you have to figure out the list of activities, right? In real life, just so you know, you have to figure out the sequence of tasks, which ones come before it. And in real life, you also need to figure out the expected time, which is expected, not always accurate. But in this course, you don't have to. Okay. So this is the example of graph PERT. It's already drawn out. This graph already drawn out. So this is a project called, start with planning stage, okay? And then after the planning stage, the people who do this project, can start removing old paint. They are painting the house. This is a project about painting the house. Okay, they start removing old paint, and Joe can get paint. So these two activities can be done together because it doesn't conflict each other. Okay, this is just how to teach you how to read the graph PERT. And after Mike remove old paint, Mike can tape windows. Put tapes around windows so that when you paint, it doesn't get to the glass on the window. Well, Mike is doing that, okay, or maybe before, after Joe's get paints, Joyce drives paints and brushes home. Okay, Joyce he brought those paint and brushes home while Mike is taping the window. So 6 and 4 could be done together also. Are you with me so far? Okay. Now while Joyce is doing that, Joe is renting pressure painter. Okay, those spray paint. You put paint in the tank and then it's high pressure and you spray it. It's fast. You don't use brush. So actually, technically, activity 6, 4, and 5 could be done together at the same time. It's just by different people. Okay? So these are just a few activities that you could be done together. And then after all is done, you see this arrow all going to activity 7, Meaning activity 7 can only be done after 6 is done, after 4 is done, and after 5 is done. Because they draw an arrow. And for activity 5, you require activity 3 to be done before you can do activity 5. Okay? And then same goes to 6. To do activity 6, Mike has to remove all paint first before he can tape the window. And then when 7 is done, after Joe prepped the machine, okay, because you need Mike Joe cover with top. Okay. It could be a not different. Mike and Joe's are cover top. Well, Joe prepped the machine. Okay. And then they can all paint a house. This is just one example of PERT. Let me see what I have next. Any questions so far? Okay. Now, let's look at this PERT graph. Okay, this is a graph. This PERT graph provides time. Okay, these are number of days. Then from start to finish activity F, I need 6 days. Okay, from start to finish activity A, I need 6 days. I need 6 days to finish F, and I need 6 days to finish D. After I complete D, then I can do B and E. After I complete A, then I can do B. So B require A and D to be done, and these are the time that's required for each of them to be done. Okay. In your when you work on the PERT activity assignments, you are required to list. Hold on, let me get the assignment out. To list which there's a critical time. Let me get the. Were you studying the graph? Because studying how I get those paths, when I look up my paper to answer the question more specifically. My question. Well, I just need the term. That's the terms. Oh, critical minimum time. Okay. Okay, so yeah, that's a good question. What is the minimum times in day it would take to finish the project? Okay, that is the most confusing questions that student can make mistake. I just now most students are like you say it has to be the least number of time, right? But to complete the project, all part of the projects need to be done. So the minimum time to complete a project actually is the longest time. So let's see how we come to get this question. Okay, so there's 4 paths that's listed. Okay, path 1 leads from start, you go to F. and then F go to G. So from activity F to G, I need 12 days. Okay, and then G goes to C, and C goes to N. That's 28 days. Okay, so this and C, to get C to start C, I need G to be done and B to be done, right? So this is one path. So when you try to figure out the minimum time, make sure you list all the paths just one at a time, like what I did here. Don't try to think too much all at once. Just do one path at a time. Make sure you cover all the paths. Otherwise, you will not get it right. And path 2, I start with A. From start, goes to A, goes to B, goes to C, and goes to N, and it takes 16 days. However, to get C's done, I already need minimum 12 plus 6 plus 4, which is 10, 22 days before I can start C, right? So even path 2 takes 16 days. I cannot actually complete C until the path 1, the F and G is done. So it actually will take longer time, right? But then let's look at path 3. From start, we go to D, and then we go to B, and then C, and then N. That takes 23 days. And path 4, from start to D to E and then end. That takes 18 days. So for a project manager, for you to do this activity, to do your assignments, when they ask what is the minimum time required to design to build a robot, after you build your PERT graph, okay, after you complete the PERT graph, that is the most essential part of your assignments. The one that has the longest time is the minimum time. So minimum time to finish this project is 28 days. Because you cannot do C until this G is done. Even though G takes longer, you just have to wait patiently. Is it understood? So the answer is 28 days. The longest time, the longest path is the minimum time for the project. Type yes if you understand what I'm saying. Okay. Now, the next terms is called critical activity. Now, if you're a project manager, if an activity takes a long time, that is your critical activities. Meaning you have to schedule your human resource. You probably have to see you can get some people from a different department to try to finish the activity faster, because those critical activities is the one who take the longer time. Or, so when the questions ask, what is the critical activity in this project? It's all the activity in the longest path. All the activities in the longest path. So, what is our longest path here? Is path 1, right? So activity F, G, C are all the critical activities. Do you get that? The rest are not critical activities. Because if this F, G, and C messed up, the project is going to take what? It's going to take longer, right? They cannot mess up. If they messed up activity A, they probably have more time to do it again. If they mess up activity B, they probably have more time. But if they mess up any of these activity, F, G, or C, the project is going to take longer. So they are critical. Okay, it's good. Let's see what else. So let's look at this question. Which tasks are dependent on activity B? Can you answer the question? Which tasks are dependent on activity B? Or which tasks or task? Singular. Which one need B to be done before it can be done? Well, the answer should be just C, okay? C is dependent on activity B. B is dependent on activity A and D. It's a flow chart, like, after B. Yeah, it's okay. The wording could be confusing. Yeah, that's why I asked these questions. And sure enough, the A and D will be in the answer choice. Okay. So C can only be done. What activity can be done after B is done? So that's another way to say it. Let's see different questions. So which activity could take longer to complete and it will still be okay? The project will still be okay. Which one can take longer to complete? A, B, C, D, E, F, G. You need to know this because when you are working on your robot project, you have to reschedule people. Like some people, you can move them from one department to the other department so that it still be okay. The project will still be on time. So that looking at this, which one do you think can take a little longer? It still will not affect the production time. Are you guys thinking? Are you waiting for me to give you answer? Rafi, are you there? So for activity that can take longer to complete but still will not affect the whole completion time. Just give you a hint, you want to start in a path that takes shorter time. Because those paths that take shorter time, if you take a couple of days longer, it's okay. You know what I mean? As long as they're not critical activity, they're not C, like activity like B, A, or D, could take a little longer and they'll still be okay. Okay? So B, A, B, or D. A, B, or D can take longer. And how long you decide to postpone those or delay those will affect your overall, you will have to recalculate the whole path, how long it takes for each path to see whether that is a suitable adjustment for your project. Okay. Let me see, what is this critical path? We already did this. The critical path is the path that takes the longest, which what we just did before. What is the critical path? The path to take the longest is path 1. And a critical path is this whole thing. Start to F to G to C to N. That's a critical path. The minimum time is the time it takes for the critical path to complete. And the critical activities are all the activities inside the critical path. I think I answered that question. So we did that. What are the critical activities? All the activities in here are the critical activities. Oh, that's it. So, any questions on PERT? You did know? You don't know? Okay. Now, once you do the activities, you come, if you understand what's critical path, critical activities, minimum time, and you work it out, carefully, then your project, your assignment should be pretty good. You can use, I will post a few like a help news items that I'll provide you a tools that you can create a nice PERT graph. Okay, you can use that, then your graph will look very beautiful, and you can adjust it easily. Okay, because PERT, your project required you to create a PERT graph. Some students just draw. I mean, draw is fine, but using technology tool is even cooler. If you don't have any questions, we'll dismiss this session. And if you have any questions, email me.